Welcome to the Drawing Board by Tau Beta Pi, where today I'll be presenting about entropy, which is a thing that happens. And I'm not going to talk much more about that. I'm going to kind of sidestep that and let's talk about spontaneity. So if you think of the common definition, spontaneity is kind of something that just happens, like someone can spontaneously decide to go buy some expensive thing. It's just a spontaneous thing. But in thermodynamics, spontaneity has a specific definition that can kind of be thought of as nature's arrow. So instead of thinking of spontaneity as something that just kind of randomly happens, think of it more as something that is going to happen eventually. So why do I say eventually? Well, we start thinking more specifically in chemistry about reactions. We have a tank of gasoline and set fire to it. That is a spontaneous process where that gasoline now just turns into fire and fumes, and it doesn't need any extra help. So for instance, gasoline ignition. We have a little bit of energy for igniting the gas, but when we have gas burning, that is spontaneous. So another way we could define specifically a spontaneous process is something that takes place without any continuous help or any extra force causing it to happen. However, as we just saw, you can definitely have something where you need some initiating force or energy to have that spontaneous process begin. Now, a spontaneous process could also be ran in reverse. For instance, if we have aluminum, you can turn it into an aluminum oxide, and that's a spontaneous process that just happens in the ground. But if you want to turn aluminum oxide into shiny aluminum, you've got to add some energy to it. So you've got electrolysis is used to recycle aluminum oxide into aluminum. So now I want to just look at a couple common misconceptions about spontaneity. One of those is that a spontaneous process is quick. Rusting is a spontaneous process and is definitely not quick. Rusting can take months. Coal forms over millions of years. Diamonds eventually turn back into graphite. All of those are spontaneous processes, but they do not happen instantly. So spontaneous does not equal fast. It just means it's eventually going to happen. It could happen very quickly, but that's not necessarily true. The other big misconception is that spontaneous processes are always exothermic. A spontaneous process doesn't have to release energy. For instance, melting of ice is actually an endothermic process. However, as it's pretty obvious to see, if you have some ice, it's going to melt in your hand. It's a spontaneous process. So think about how spontaneity is something that's eventually going to happen. It's nature's arrow, but it could be very, very slow, or it could actually take energy to happen, be an endothermic reaction. So with those pieces in mind, we can think about what is the actual criterion or way of quantifying spontaneity. Well, when we're thinking about how ice melts, we know that has something to do with temperature, because obviously that has to happen above 0 degrees C. You can also think about how enthalpy is involved. So putting that together, we finally end up with our actual original term, entropy. So entropy is another state process like enthalpy. So we have to write it in terms of the change or the delta. So most prominent equation is the fact that entropy, which is an S for some reason, I'm just going to pretend it's because of spontaneity, you know that the change in entropy is equal to the change in enthalpy divided by the temperature. And all of this has to be for a certain system or a place that it's happening. We could have an entropy change for a specific reaction in a container, or we could have entropy changes outside of the container. So usually we'll call that delta S inside of the system, and we would have a delta S in our surroundings. And we can also think of in the entire universe, there's a change in entropy. And we'll get to that a little bit more later. So now that we have a term for entropy, we can start thinking about like when does it increase or how do we actually think of it happening. So one way to think about entropy is that the more ordered a system is, so an ordered system has less entropy, and then in the opposite case, a chaotic system or a disordered system has more entropy. But it's not quite as simple as saying like a messy room has more entropy. You also can think about the probability involved. So for instance, if we have a couple dice, those have a fewer number of rolls. So it's more likely that a couple dice are gonna land with the same number coming up. But if we have a bunch of dice, it's going to be way less likely to end up with the same number coming up. So in a similar way, if we have more particles in a system, there's going to be way more going on, and there's going to be more randomness or more entropy involved. So actually applying to chemical processes, 3 examples of times when entropy increases are: 1 is when we have an increase in temperature, because when we're increasing temperature, we're increasing the energy in the system, and we're increasing all the different ways that those particles could arrange, and increasing the probability of disorder or having different numbers show up on dice. Another way that entropy increases is if we have a less stable phase, so basically melting or boiling. So a solid is more ordered than a liquid because it has a crystal structure and it's pretty, it's in the name, it's solid. And a liquid is more ordered than a gas, which is all bouncing around. So when we melt or boil, we're increasing the entropy of the system. And then a third example is when we increase the number of particles. While we're thinking about chemistry, classic example is just having some reaction that starts with 1 mole and then we end up with 2 moles. So if we have reactions that result in a greater number of moles, we have more particles, and so we're going to have more entropy in that reaction. So now let's take a break from entropy and think about the 3 laws of thermo. The first law, which you might remember, is basically that energy is conserved. So you might have energy go out of one system and into another or change form, but it's still going to be conserved. So if we look in terms of enthalpy, we can say that the change in enthalpy of the surroundings of a system is equal to the negative of delta H of the system. So now looking at the second law, this is where we start thinking about entropy again. Because the second law says the change in entropy in the universe, that is going to always be positive. We're always having entropy increased in the universe. And this is due to spontaneous processes. When we have a spontaneous process, it increases entropy, and spontaneous processes, by definition, are going to happen in the universe. So we can rewrite this equation by realizing that the change in entropy in the universe is also equal to the change in entropy of a system and its surroundings. So that's going to be greater than 0. Then if we squeeze this in and plug back in our equation for entropy in terms of enthalpy and temperature, we can also say that delta H of a system over temperature of the system plus the delta H of its surroundings over the temperature of its surroundings, that is also going to be greater than 0. That's just an application of the second law. And then the third law is basically saying that entropy approaches 0 as temperature approaches 0. So you can think of crystals that are perfect, where they're at absolute 0, no vibration. Theoretically, we have no entropy involved in those crystals. There's the overview of those 3 different laws of thermodynamics. And let's take a closer look at the second and third law, since they directly relate to entropy. So here's an example applying the second law. So in this problem, we're saying that 1 mole of water at 0 degrees Celsius and at 1 atmosphere is melting because it's at 0 degrees Celsius and because it's in your hand, which is at 37 degrees. We're also told that the delta H of fusion, so in other words, the enthalpy involved in freezing water, is plus 6.01 kilojoules per mole. It's an endothermic reaction because the heat of fusion is positive. So in this problem, we're going to use the second law to find delta S of the system, delta S of the surroundings, and delta S of the universe. The first step is finding delta S of the system. So going back to the definition of entropy, we can say that it's the delta H of the system over the temperature. We're given the delta H in the system, so it's just that 1 mole times that 6.01 kilojoules per mole, and we have it positive because freezing it is an endothermic process. Then we have to divide that by 0 degrees, but we can't divide by 0, so what's going on? Remember, we always have to have temperature in absolute units. So we have to add 273 to make that Kelvin. And when we calculate that out, we end up with 22 joules per Kelvin, the unit for entropy. So there's our delta S system. So then going on to delta S of the surroundings. Well, in the surroundings, we have delta H of the surroundings over T of the surroundings. And in this case, we still have 1 mole, but now it's times minus 6.01 kilojoules per mole. Because the surroundings aren't melting, the surroundings are giving up the enthalpy to melt the water, so we have to make that negative. And then the surroundings are also hotter than the melting water. So we have to put down 37 degrees Celsius plus 273 to get Kelvin, and we plug all of that in, we end up with negative, because we're losing entropy from the surroundings, negative 19.4, still in joules per Kelvin. So now we've got the system and the surroundings enthalpy changes, and now we have to find the change in entropy of the universe when this water is melting. So in order to do that, we just have to go back and add those values together. So we have delta S universe equals delta S system plus delta S surroundings. It ends up being 22 minus 19.4, which is equal to 2.6 joules per Kelvin. And that is a positive number. That's showing us what's said in the second law, which is if we have a spontaneous process, that is causing a positive change in the entropy of the universe. So going back to the third law of thermodynamics now, remembering that theoretically at 0 degrees Kelvin, we're going to have zero entropy. So using that a little more practically, we have what's known as the standard molar entropy, or delta S naught of reaction. So this value is basically a measurement at a specific temperature and pressure, and usually that's going to be like 25 C and 1 atmosphere. Some standard temperature and pressure. Your mileage may vary in what you actually have for those values. But actually applying this at delta S naught of the reaction is equal to the sum of all of the individual standard enthalpies of the products in a reaction, and all that times the stoichiometric ratios of each of them, minus the sum for all reactants. So all of these S naught values you can look up in tables. So for instance, if we had a really simple example of just like A going to B, we could look up in a table and say, well, compound A has a standard molar enthalpy of 2 joules per mole Kelvin, while B has a standard molar enthalpy of 1 joule per mole Kelvin. And so if we wanted to actually find delta S naught of the reaction, these are just 1 mole going to 1 mole, so we can not worry about the rest of it and just say it's going to be the product minus the reactant standard molar enthalpy. So it'll be 1 minus 2. So this will be a negative, so this is a non-spontaneous process. It's minus 1 joule per mole Kelvin. So the reason why we can do this, again, is because we have a standard for 0 degrees Kelvin. It's theoretically 0 entropy. So we can also have a baseline point with non-zero values and do a similar thing where we take these values and just apply it to a more complicated process than just increasing temperature. So thinking once again about spontaneity, which is kind of our way of thinking about what entropy is. You might want to think about, is entropy the only thing we have to worry about? Is there perhaps an easier way where we don't have to measure these standard molar entropy values? Can we find a better way? And the answer is yes. We don't have to find delta S of the universe if we are able to find another value that we can compare different reactions to. And that value is known as Gibbs free energy. And we'll show that as, once again, a state function. So it's G. So our delta G is based upon our entropy, but also our enthalpy and temperature. So specifically, it's going to be delta G is equal to delta H minus T delta S. And if we do a bunch of substitutions and rearrange stuff, we can also find that delta G for a system is equal to minus T times delta S of the universe. And look at that, we've got our delta S of the universe that is determined by our delta G of the system. So if we know what's happening in a reaction, then we don't need to figure out this more complicated value. So briefly looking at how the change in Gibbs free energy can be used, we can think about all the different types of situations we have. If we have just that constant temperature, where we're only thinking about that enthalpy and entropy, we have a spontaneous process, we have a non-spontaneous process, and we have equilibrium, where it's neither spontaneous nor non-spontaneous. So for spontaneous, we know, thinking about our definition of spontaneity, that the delta S of the universe is going to be greater than 0. Because in the definition for Gibbs free energy, we're doing minus, then the delta G is going to be negative or less than 0 for a spontaneous process. So this is another way we can figure out, is it spontaneous? Well, let's check if delta G is less than 0. So then filling out these other examples, if we have non-spontaneous process, delta S of the universe is going to be less than 0, so therefore delta G is going to be positive. And at equilibrium, delta S of the universe is 0, and that's the same thing for Gibbs, because negative of 0 is just 0. Now if we want to look at not just at constant temperature, we can break down this equation in a different way. So think about how delta G is equal to delta H. So we can think about what is that sign of delta H, and think about minus T delta S. We can think about what is the sign of the delta S. So if we have a negative delta H and a positive delta S, that means that it is spontaneous for all temperatures. If we look at the opposite case, positive delta H minus delta S, this is never going to be a spontaneous process. If we look at them both negative, it will be spontaneous, but only for low temperatures. Another way of saying this is an enthalpy-driven process. And if we have both of these positive, this will be spontaneous only for high temperatures. You might also hear this as an entropy-driven reaction. So one last way we can apply Gibbs free energy to reactions is, once again, we have a standard value. So we have the standard Gibbs free energy of formation. So this is going to be shown as delta G naught F. So just like before, we have the standard Gibbs is equal to the sum for all of the products and their Gibbs free energies of formation. And just like for entropy, it's going to be the products minus the sum of all the reactants. So once again, we can have some sort of reaction, and we have all these values at standard 25C, 1 atmosphere, or something like that. And we'll have some compounds and some values for the Gibbs free energy values. And we can use those to figure out what's going to be that delta G naught of the reaction. So now let's look at a summary of what we've covered. We've taken the broad concept of entropy. We've thought about it in terms of spontaneity, where spontaneous process is just something that will happen eventually. It's not quick, not necessarily exothermic, but it is nature's arrow. Entropy can also be found with a very important equation of delta S is equal to delta H over temperature. We also talked about the different laws of thermodynamics, how especially the second and third laws are directly related to entropy. And we finished off by talking about Gibbs free energy and how this is a simpler way of determining if a process is spontaneous instead of having to deal with the entropy in the universe. So hopefully that has all been helpful. This has been the Drawingboard by Tau Beta Pi.